Hello, this is Archit Mukunda, and this is my video submission for homework 1 for the course Design and Analysis of Reconfigurable Systems. And I'll be demonstrating the design and verification of 1-bit full adder using both schematic and Verilog, and then analyzing the results of parametrizable n-bit adders. So these are just the laboratory objectives, summary, pre-lab, and two requirements for the homework submission. And then this is the schematic of a full adder that we are going to design using Quartus Prime Lite. And then we'll be looking at the waveforms using Questa simulator. Yeah. So coming to the schematic diagram. So I've just created a full adder schematic file, and then I've just dragged and dropped the gates, the two XOR gates, two AND gates, and one OR gate, and the input pins and the output pins using the symbol tool that we can see here. So this is the tool. Then we basically just use these libraries and then just drag and drop them. Yeah. And then I've used the orthogonal node tool for the connection of the wires, and then once everything is done, we just compile this and get the reports. So I've already compiled this, and I've also generated a Verilog file for this schematic, so I'll just be opening that. So this is the schematic diagrams Verilog file that was generated earlier. So as we can see, this is a full adder hierarchy, and then coming to the files, this is the full adder Verilog file where I've just created a module called full adder, and then I've defined the input wires and output wires, and then I've just assigned the operation for these. So saying that assign synthesized wire 4, which is A XOR B, and all the implementations, and then coming to the test bench. This is what we are going to use for testing the Verilog code that we have written. So these are the test cases that I have just briefed. So let me just give compile. So this is going to take a little amount of time. So as we can see the indicator here saying it's 0%. So and we can see the progress here. So the analysis and synthesis is running, and then that's done. So you can also see the flow summary. So this has total pins of 5 in count, and then coming to the summary, again the same, and then we also see the fitter, but fitter is still compiling, so we'll just have to wait for the report. And then yeah, in the meanwhile, so coming to the first part of the documentation or report, which is the schematic entry. So I've just shown the schematic diagram here, a screenshot of that, and then I've just basically explained what is a full ladder design, and then again just the way of simulating the schematic diagram by generating a Verilog or a VHDL files, and then and coming to this fulladder.sdc, this is the file that I used for generating the timing constraints or a timing analyzer. So it basically just starts and stops the clock, as you can see with the code. Then yeah, we are still waiting on the report to be compiled. Once the report is compiled, we'll just look at the reports and then We just analyze it and then we use the tools section and run simulate, which opens the Questa simulator through the Quartus Prime, right? So yeah, I see the fitter place and routing reports are ready. So which we can see here again. So the if you look at this, we have total 32,000 of 32,070 ALMs which we can be using, but we the system just used two, and then total pins that we can use on the board on the virtual board is 457, but we have only used five as it's a 1 bit full adder. It has three inputs and two outputs, so five pins. And then yeah, everything is ready. As we can see, there are zero errors and we just neglect the warnings. So coming to the timing analyzer, we see at this, and then we also say this: the design does not contain any failing setup paths. The worst case rack is 3.427, so that's the thing. And then we also see at this SDC file list and then clocks. And then once the compilation is successful and once we get zero errors, we just do this RTL simulation. So this opens Questa simulator through the Quartus Prime, where we'll be looking at the waveforms of the code and the test bench. So basically the test bench is testing the Verilog code using those test vectors. So these are the test vectors that we have used. So I see it's still loading. Yeah, these are the pin signals that we have, and then the waveform is still loading here. So if in case the waveforms are not loading here, by default we just select these and then let me just show. So basically we just select every pin and then we do this add to wave selected signals, just in case if it's not default present in the wave window. So this is already present and the simulation is done. So we just zoom full. So coming to this verification of how our 1 bit full adder is working. So looking at the test vectors and cross verifying with the truth table, we'll just be knowing that. So at 0 nanoseconds to 10 nanoseconds, the inputs are 000, so we'll be getting the output as 00. And then from 10 to 20 seconds, it is 001, so our carry out will be 0, but S will be 1. So as we can see that, and then again from 20 to 30 it is 010, so it is 10 again, so the outputs doesn't change. So just verifying everything looks good, and then the system stops wherever once the operations are done. Yeah, this is for the schematic Verilog part. So we'll just close this. Yes. And then once our schematic Verilog and Verilog or VHDL code with the test bench are successfully simulated. So coming to this, yeah, then simulate the one which showing that it works, including here. Okay, that I've already included the test cases or test vectors, and I've also given the time interval for my waveform output. So I've also attached a screenshot for that, and then yeah, and then coming to the next part, which is the RTL implementation. We'll just close this project and then open the full adder RTL project. First year, the one bit with the schematic editor, it used XOR hand and OR gates. That's the same thing, yeah. So coming to this is the wave RTL Verilog code and the test bench code. So again, I've used the same test vector. So this is pretty much the same. Again, compile it, everything successful. Then open the RTL simulation tool and then look at the waveforms, verify it again. So that's done. So next we'll be going to the RTL design where we'll be using two approaches. One is behavioral and then one more is structural. So we'll just start with behavioral. So in this, I've created two parametrizable n-bit adders in Verilog. This is the behavioral model, which uses the simple plus operator to describe the addition. This lets the synthesizer choose the best implementation. And let, let us just check the Verilog code. So I've just used the plus operator, yeah. And then I've also made this flexible so that when we are doing it for the 4-bit, we just enter it as 4, n equal to 4. And then when we are verifying it for the 8 one, we'll be doing it for 8 and then we'll be changing it to 16. So let us just see this. So once we have written 4, let me just do it for the 8. Yeah, once this is done, we just save it and then we go to the settings and then we'll have to write the macro. So this is telling that the number of bits are 8. So once this is done, we just give compile. So again, this is going to take some time. So let us just go to the report. And then once we do it for the 4, 8, 16, so yeah, we are going to do this. And then first we are approaching on the behavioral, then 4 bits, 8 bit, 16, and then we do the structural. So we are basically comparing the ALMs used and then the critical path using this maximum slack time that the each operation or the each 4-bit operations taking. So we'll be getting the results on this. So we are just doing this for the behavioral 8. Yeah. So our analysis synthesis report is ready, so we can just jump to this. So we can see that for a 8-bit full adder we'll be having 26 pins. So for the 4-bit it will be different, and then for the 16 bits again it's going to increase. So coming to this part, so these are just verification of those, and then what test vectors would you use in case of having a test having to test a 4-bit adder and a 8-bit adder. So we just use these. So if it's a 4-bit adder, we'll be having total 9 inputs and then 5 outputs. So the test vectors would be 2 to the power of 9, so which is 5 and 2 test vectors. And then for a 8-bit adder, it will be 17 inputs and 9 outputs. So it will be 2 to the power of 17, which is 131072 unit unique test vectors. And then this is a report of utilization for the schematic uh, generated Verilog and Verilog or VHDL file. I've used Verilog, so these are mine. So when I see that 1-bit add a schematic analysis and synthesis report, which is that which is this report for the Verilog code for the schematic generated files. So I have my system used 2 out of 2 and then 2 after 2, and then flip-flops used as 0. Inputs, sorry, IOs are 5 and 5, DSP 0, BRAMs 0. So, and then critical path from the timing analyzer is this, which we have got this in the timing analyzer feed or the report feed. So, and then we use this for the computed maximum frequency, which is Fmax equal to 1 by TPD. So 1 by 6.573 is 152.14 hertz, megahertz, yeah. So this is just the ChatGPT analysis of the result for our homework. And then this, we have, we are just doing this. So yeah, the reports are ready. So as we saw, the ALMs used are 5 and 5 for the behavioral, and then coming to the timing analyzer, so it uses 1.576, so which is 10 minus 1.576, which is 8.424. So that is the critical path. So similarly, if we are doing this for the 4-bit one, 8-bit one, 16-bit one, we just fill this thing, and then we can also run this simulation. And this is the behavioral model, and then we'll also be looking at the structural model. So in the structural model, it's built using the 1-bit full adder as a component, which is then chained together in this main file using a generate loop to create a ripple carry adder. So that's the structural model. So if you're looking at the Questa, so the waveforms are just loading. If they're not, we'll just add it with this. So these are the waveforms. We just add these. So actually it's still loading. So because it's a 8-bit full adder, it's taking some time. So by default, it's not added to the wave window. So we just add it to the wave. Yeah, selected signals. Then we just write run all, saying that we need this thing formatted. Yeah. So because we have not uh, written any test bench, so we will not be able to see the waveform for this. So if you see this, there is no test bench in the files hierarchy. So that is why we are not able to see the waveforms in the Questa simulator. So, so we have already checked the waveforms thing with the Verilog code, which we have generated with the schematic. So I'm just closing this and then opening the structural model. So as said in this, I've created a loop that generates a triple carry adder model. Yeah, so this is the full adder 1-bit. So just see this. So, and then this is the structural model. used for this. Again, this is flexible. You can give n equal to 4 or n equal to 8 or n equal to 16 as per the requirement from this question. So once we have got everything, we can just look at the tabular and know that what is happening to the ALMs and critical path for changing the number of bits for the same operation. So So basically I've compiled both designs for 4, 8 and 16 bits. These are the final results. As you can see, the logic usage increases for both as they get wider. The biggest difference is the performance. The structural address critical path gets much longer as we go to 16 bits. So if you see this, the ARMs used are way above what others are using, so which is 19, and then reaching almost 11 nanoseconds too. This is because the carry as to ripple through all the logic cells. The behavioral adder performs better, especially at 16 bits, because the synthesizer can use the FPGA's dedicated fast carry hardware. This proves that for arithmetic, a behavioral description gives a much more effective result. Effective or an efficient results, yeah. And then these are just the discussions about the resource usages. And then the conclusion for my work is the assignment demonstrated the full FPGA design flow and showed that a high-level behavioral coding style yields superior performance for an arithmetic circuits. Yeah, in comparison to the structural model. So, thank you.